probabilities. Hello everyone, this video will be on probability distributions and how to use specific functions in RStudio to generate answers to questions on probability. First up, we'll look at the D binom, the P binom, and the R binom functions. The D binom function can be used to plot the values of random variables which follow the binomial distribution and also calculate the probability that the random variable assumes a specific value when it follows the binomial distribution. Next, the p-binom function will be used to graph the cumulative distribution function of a random variable following the binomial distribution. The r-binom function is used to generate random numbers which follow the binomial distribution. Similarly, the dpoise, the dunif, and the dnorm functions can be used to calculate the probability of any random variable assuming a specific value according to the Poisson, the uniform distribution, and the normal distribution, respectively. That's why the names are POIS for Poisson, UNIF for uniform, and NORM for norm. Then we have the PPoise, the PUnif, and the PNorm functions. These functions graph the cumulative distribution function of any random variable which follows the Poisson, the uniform, and the normal distribution functions. And then we have the rpoise, the runif, and the rnorm functions. These three functions are used to generate random numbers which follow the Poisson distribution, the uniform distribution, and the normal distribution. And we also use a specific function called as the set seed function. The set seed function is used to initialize the generation of random numbers by specifying a particular value within the brackets. And this set.seed function is to be followed by any of the random number generating functions, namely rbinom, rpoise, runif, or rnorm. Uh, Apart from setting the initial value of the random numbers generated to a number of our choice, the set.seed function also helps us reproduce the same set of random numbers already generated. Now we'll have a look at a few programs which uses these functions to solve problems on probability using the RStudio. All right, before we move to the examples on how to use these functions, I'll just give you a brief introduction about the syntax. The p-binom function, which is used to calculate the cumulative distribution value for a binomial random variable, takes three arguments: the value of x for which the cumulative distribution is to be found, the number of times the experiment is conducted, which is n, and p, the probability of the desired outcome, which you call as the success event. A similar syntax is used for the d-binom function, which is used to calculate the exact probability that the random variable assumes the value x. The trial is repeated n times, with the probability of success being p. The r-binom function takes a slightly different syntax. It takes in the same values of n and p as the last two arguments. The first one, though, denotes the number of random numbers to be generated. It may be 1000, it may be 500. All these random numbers will be generated using this function, and these random numbers will follow the binomial distribution. A similar rule is followed for the ppoise, dpoise, and rpoise function, which are used for calculating probabilities and generating random numbers under the Poisson distribution. So the first two functions, the ppoise and the dpoise, are used to calculate the cumulative probability and the exact probability of any random variable x following the Poisson distribution. They take the same set of arguments as input, x, which is the exact number that is required in the question, and lambda, which denotes the average of the Poisson distribution. The rpoise function is slightly different, like we saw in the r-binom function. It takes as input lambda, which is the average of the distribution, and the total count of random numbers that are to be generated under this distribution. And then we have the p norm, t norm, and the r norm function. The p norm function will take as input the exact value at which the normal distribution probability has to be calculated. In addition, it will take the average and the standard deviation of the corresponding distribution. The same happens for the d norm function. As usual, for the r norm function, the first argument is the number of random numbers to be generated. It is the count of the total number of random entries to be generated, which follow the normal distribution. This is followed by the values for the average and the standard deviation. And for the uniform distribution, we take as input the x, which is the exact number that has to be calculated under the uniform distribution, followed by min and max, which are the lowest and the greatest values that the variable can assume under the uniform distribution. If you can recall, there are two constants, namely a and b, associated with the uniform distribution. The min and max will refer to those two values. As usual, the p-unit function also follows the same syntax. The r-unit function follows a different syntax in which the first argument will reflect the total number of values to be generated under the uniform distribution. The most important function that I introduced in the previous slide was the set seed function. The set seed function ensures that the same set of random values are generated every time the R binom, the R poise, the R norm, and the R unit functions are used. So to generate the same set of random numbers, we use the set seed command. The set seed command takes in only one positive integer as input, which is used as the seed to generate as many random numbers as required. How are these random numbers generated? That may depend upon the choice of the programmer. There are many methods to generate a sequence of random numbers. We don't bother about the method of generation. We are only focused on the starting value, which is the seed. All right. In this video, once again, we'll look at a few programs which will use the specific functions on mathematical probability distributions using the software function called as the RStudio. First up, we have the problem to calculate the probability that a random variable takes the value 3 when it follows the binomial distribution of size 8 and the value of the success is 0.6. So this is denoted by the two lines of code which assigns the value n is equal to 8 and p is equal to 0.6. Then we use the dbinom function and calculate the probability that x assumes the value 3. The answer is generated as 0.123 here. The answer is generated as 0.123863. Next, we repeat the same calculation for a Poisson variable, which takes up the value of lambda as 2. So the parameter of the Poisson distribution is the lambda 2. So we assume lambda is equal to 2. And we calculate the chance that a random variable assumes the value 5, which is mentioned in this line of code. We use the p-poise function, the probability of a Poisson distribution. The answer generated is 0.9834364. And then we try and generate the histograms which represent the uniform distribution and the normal distribution. So first up, we use a set.seed function to initialize the random numbers generated to start from 123. And then we run the runif function to generate 1,000 such random numbers. And then we we start plotting the histogram by using the HIST function. The corresponding graph is displayed on the screen. This is the histogram. We can repeat this for the normal distribution. We use the set.seed function and the rnorm function to generate random numbers that follow the normal distribution. Once again, using the HIST function helps us get the histogram of the normal distribution. You can see that the graph, the histogram obtained follows the shape of the normal distribution curve. And then we can generate random numbers using the Poisson distribution and use simulation to calculate its mean and variance. So we first generate numbers using the RPOIS function, and we use the mean of data and the variance of data to to define the mean and variance using simulation. The mean and variance appear to be 2.96 and 2.91 for this case. And you can see that this coincides with the actual lambda. The lambda that we defined is 3, and the lambda that we arrive at using simulation is 2.967, which is pretty much close enough. We repeat the same thing for the next problem. We try and use simulation to guess the mean and variance of a binomial distribution after generating 1,000 random numbers with an average of 10 and a probability of uh, 0.5 being the success. Using the R binomial function, we generate 1,000 random numbers. The result that we get are 4.975 for the average, which is close because if n is 10 and p is 0.5, then the average is np. It's 10 times 0.5, which is 5. The result that we get using simulation is 4.975. That is quite close enough. The variance is npq. So 10 times zero point 0.5 times zero point 0.5 is 10 times 25, which is 2.5. And the simulation result is also quite close to 2.5. So both these answers make sense. And then we discuss how to plot the cumulative distribution functions and the probability distribution functions using the D binom and P binom function for a binomial distribution. Executing this line of code and using the bar plot function and the plot function gets us these two graphs. The first one is the cumulative distribution of the binomial distribution, and the second graph is the plotting of the binomial distribution as generated by the D binom function. This will represent a binomial distribution. We can repeat the same for the normal, uniform, and the Poisson distribution. Next up, we plot the distribution function and the cumulative distribution function for a Poisson variable with lambda as 4. Running this code helps us plot this. The corresponding distribution function has this as its bar plot and this as the cumulative distribution plot. We repeat this again for the uniform distribution. We set b as 1, and the value of b of the uniform distribution is set at 1, and this helps us define the distribution function in this way, followed by the cumulative distribution function, which is the other graph that we have. The other graph helps us define the cumulative distribution function. And the last thing that we'll discuss here regarding graphing the distributions is the normal distribution. Normal distribution, you can see that a very nice bell-shaped curve is arrived as the answer, which is reflective of how the normal distribution looks like, and its corresponding cumulative function will look in this form, will have its graph in this form. And then towards the end, we also discuss how to calculate the probability. So when the average is 0 and the standard deviation is 1, then the p norm function can help us calculate the probability of any random variable which lies between -1 and +1. Executing this function will return the answer as 0.6826. If you have your scientific calculators, you can verify that the area on the graph between -1 and +1 is 0.6826. The p norm function helps to generate the answer very easily. And the last thing that we'll have is to find the average. We know that finding the average, according to the definition, is to integrate x and the p of x here, and this will also help us get this answer. That's it for this video. I'll follow this video shortly with another video on similar functions. Thank you. So that's it for the video. We have discussed some important functions based on RStudio to calculate probabilities of various distributions which are usually used in statistics. I'll follow this shortly with another video on testing of hypotheses. Thank you.